Okay, quick tutorial walking you through how to do a couple different types of t-tests in Excel. So I've got a couple different types of data that would require different t-test types. So the first one on the left showing you water quality data. These are concentrations of lead in ppm for 5 replicate samples measured identically across 4 different labs. So the same samples measured by 4 different groups or 4 different analysts. And so when we're thinking about how we could answer a question like, is the mean value for lead concentration measured by lab A statistically different from the mean value measured by, say, lab C, we would need to employ a t-test. And since these are identical samples being measured simply by different analysts, then we'd need to run what's called a paired t-test. So to run a paired t-test, you're just going to go up to Data, and then all the way to the right there should be these plugins. You should have data analysis already added. If you haven't, Google the version of Excel you're using and the operating system that you're using and figure out how to add the data analysis package. So you open this, you'll have a variety of statistical tools at your disposal. Scroll down, you'll see 3 different t-tests. You'll have the paired, you'll have the 2 sample with equal variance, and 2 sample with unequal variance. We want this first paired version. Click OK, and then in the dialog we are going to select the 2 ranges of data that we want to compare, and typically it's easiest if you select the one with the largest mean first. So just click this button. I've already selected this, but I'll select it again, and then for our variable 2 range we're comparing it to C here, so I'll select those first 5 values. Hypothesis mean difference in chemical analysis is always going to be 0, because what we're really trying to evaluate, the question is any difference at all between these 2 sets of data statistically significant at whatever the confidence interval that we're determining that over. And so we'll leave this blank, then that assumes 0. Alpha is 1 minus that confidence interval. So if we're trying to determine this at 95%, which would indicate that if there were a difference in the mean values between these 2 labs, A and C, that at 95% confidence, that means any difference that we would find there would only be a 5% chance that that's simply due to random error. And so in chemical analysis, we're often doing things at 95% confidence. So we'll leave this as default, and we can set this either to output a range in this same sheet, or new worksheet ply is going to create a new tab down here. That's what I'm going to do. Click OK, and you can see that it generated sheet 5. We're in a new sheet now. I'm just going to double click to expand these. So we have our 2 variables. So these were the 2 labs, A and C. You can rename these if you want. It doesn't really matter. So there's lab A, there's lab C. It computed the average and the variance, and it told us how many number of measurements, replicates there were, 5. None of that's really that useful. What is useful is this section of information down here. So the t-stat is the computed t-statistic, and this is the value that we then need to compare to the tabular value, the value that you would look up in the t-table. Remember that the criteria for statistical significance, meaning that there actually is a real difference that's not simply due to that 5% random error, is when the computed t-statistic is greater than the table value. So we're typically using 2-tailed tests. So here's the t-critical, this is our table value, so we're comparing this value to this value. And remember, this is a 2-tailed system, so it is a normal distribution, so a negative t-statistic. So we're really looking at the absolute value of that and comparing it to this. This is much smaller than this value, and so these 2 means of lab A and lab C are not statistically significant in their difference at 95% confidence. Okay, so that was a paired t-test. Let's look at a different set of data here. So these data come from a textbook that shows Ray Lee's original data in trying to compute the atomic weight of nitrogen. So he had done it 2 different ways. he'd filled up some glass vessels and actually weighed them. And so this is just from air. He'd weighed those aliquots of air and gotten these masses. And then another one was he took a sample that contained nitrogen and he decomposed it, and he measured the mass of that decomposition and did some stoichiometry to work that out. And so what we're trying to figure out are the differences, or the mean values of these two sets of data, which I can just compute very simply. Are they statistically significant in their difference, in the same way that we were asking that question for the previous set of data? So let's make sure this is capturing all of that. Pull that down. Okay, so are these two means statistically significant in their difference? Remember, the criteria for the pair t-test was that the exact samples are being measured by different analysts or different groups, but the important aspect of that is the sample is common to the analysts. Similarly, if you had the same exact samples and you measured them by two different techniques, that would still be a paired t-test in your evaluation because it's the same samples just being measured different ways. In this case, it's slightly different because we have air samples and we have solids that were heated and decomposed. So these are fundamentally two different samples, so the means are not generated for the same samples. They're generated for very different things. And so in this case, we need to run a different type of t-test. So remember, we have two options here. We have these two other t-tests for two samples. One assumes equal variance and one does not. So before we can choose the correct t-test, two-sample t-test, we first need to determine, are the standard deviations or the precisions of these two measurements, are they coming from the same population or not? If they are, then we can assume they're pooled standard deviations. If they're not, then we can't pool them. And so to determine if the precisions are the same or not, we do an f-test. So f-tests we can retrieve again from the data analysis package. We just select f-test to sample for variances, click OK, select one of the ranges as your variable 1, the other range as your variable 2, select 0.05, that's the default, and then generate a new worksheet ply. And so that's going to open up this new table, and you can see that it computed actually the two values here, it labeled them, and then it computed our F statistic and the table value in the same way that it did for the t-test. And so our F statistic is smaller than our tabular value, the F critical. And so by the same criteria as we used for the t-test, this is not statistically significant or different, which means the standard deviations for those two sets of data can be pooled. So that means we can use, if we now go to evaluate our t-test, we can go down to two sample assuming equal variances, because the f-test told us that the variances were not statistically different, at least at 95% confidence. So we'll select OK here, do the same thing again. We'll grab these data one at a time for each of those variables, allow everything else to be default, and we'll generate a new worksheet plot. Okay, that gives us an output that looks like this, very similar, except this was the result of a t-test two sample assuming equal variances. Again, the output of the data looks almost identical with different values. So here's our computed t statistic. It's quite large, which means that the means of these two values, the differences there, are pushed out at roughly 20 standard deviations from the population mean, whereas the t-critical, the tabular value for the two-tailed test at 95% confidence, says it should only be out at about 2. So in this case, we would conclude that the mean value from the air analysis is statistically different with significance at 95% confidence from the mean value determined by